In the last few videos we have talked about integrated rate laws. We have derived the rate law, integrated rate law for a zeroth order reaction, for a first order reaction, and then we have introduced the concept of the half-life. We can continue our study or exploration of integrated rate laws by taking a look at how you would derive the integrated rate law for a second order reaction with one reagent. Okay, so we again are looking at this expression A towards B, and we do measurements of the rate law, and we determine that the rate law is equal to the rate constant times the concentration of A, but this is a second order reaction, so that power that you have right here is 2. Okay, it's a second order reaction with one reagent. At the same time, we know that the definition of the rate is simply how the concentration of reagent falls as a function of time. Okay, so equating these two expressions is going to give me a differential expression that we can then integrate to obtain an explicit dependence of the concentration as a function of time for a second order reaction. Right, so let's do that once more. That is the definition of the rate, and then we can equate this to our rate law. Okay, and this is what we have to solve. It's a differential expression that we're going to integrate first by separating variables. Okay, so I put concentrations on the left-hand side of the expression, and then time at the other side of the expression. Okay, differential of t. Okay, I can change the sign of this, and then that, and I'm ready. Now I'm ready to integrate. As always, we're going to be integrating this from the start of the reaction where the concentration of A is A sub naught to any time where the concentration can be anything, and then time will be will go from 0 to t. Again, this is exactly the same as what we have seen before. You would be integrating between time 0 and time t. That is going to factor out of the integral, so you can simply write this integral as time 0 to time t, okay, like that. And we've already seen that the integration of this simply yields minus kt. Now, what about the integral of differential of a over a squared? Well, this is the integration of a polynomial, which you can see that is going to yield minus 1 over the concentration of A. Okay, and that is going to go from, we have to evaluate this from A naught to A. Right, so again, to evaluate these limits, we simply plug this value into this function and subtract whatever happens when we plug that value into the function. Okay, so we do this is equal to minus. Again, we plug concentration of A in the function 1 over A, so that's what we obtain. And then subtract whatever happens when we plug this 1 over A naught in that function. Okay, minus 1 concentration of A naught. Okay, and this is equal to the right-hand side of the expression, which is minus k sub t. Okay, so these two negative signs cancel each other out. And then we have that the integrated rate law for a second order reaction with one reagent is going to be equal to 1 over the concentration of A over 1 of the concentration of A at time 0 plus k sub t. Okay. Much as before, what we could actually do is then try to solve this for the concentration of A to see the functional dependence of the concentration of A on time. This turns out to be a little bit complicated for this particular case, and we're actually not going to do it. But suffice it to say that if you were to do it, what you will see is that the concentration of A as a function of time is not a linear function. Okay, it should have a dependence that is somewhat like that. And in the book, you actually have a comparison for how this decay of the concentration of A on time is similar and different to the exponential decay that you observe for a first order reaction. But again, this is actually quite different from what you obtain for a zeroth order reaction, where this should be a linear dependence. Okay, so this is the integrated rate law that we're going to be using in problems for a second order reaction with only one reagent. In the next video, we're going to explain what is the integrated rate law for a second order reaction, but not with one reagent. You will have two reagents.